Okay, hello class. Welcome to section 2, chapter 6. We're looking at recursive sequences or recursive procedures in this lesson. And the first question that you want to consider is, what does this word mean? What does recursive mean? It sounds like it might be prompting you to do something you shouldn't be. To recurse, maybe to swear again? No. Okay, so that is not the meaning of the word. And you probably have not used this word before, so that's why we're going to go to the Oxford Dictionary and have a look just to see exactly what the definition of this word is. So, okay, here you are at oxforddictionaries.com, and we see a couple definitions. And we wanted to point out that well, the one that would apply to us in a math class would be the first one, characterized by recurrence or repetition. In particular, we're looking at involving the repeated application of a rule. Okay, so there's going to be a procedure involved, as the definition suggests, and this is a bit in contrast with what you've just looked at in the first section of chapter 6, which was explicit formula. So this is going to involve terms related to other terms, not explicitly in relation to the term number, but in most cases just applying some kind of a mathematical rule or function on a term or previous terms. All right, so we're going to return to our lesson note here in Smart Notebook, and these are the characteristics or properties of a recursive sequence that you're going to want to observe, take note of here. The first one is that initial term or terms must be provided, and the second condition is that we need to have a rule or procedure that is going to generate the other terms, the successive ones from the previous term or terms. All right, so what does this all mean? Let's get an example of some questions that you might want to be solving here. All right, so there's a couple types of questions that we could solve. And if you look at question number 1 here, it asks you to write the first 4 terms in each sequence. And the second type of question that is fairly common with this topic is, given a sequence, trying to model the formula, the recursion formula that describes all of the numbers. Okay, now just keep in mind when we use a repeated 3-dot pattern there at the end, that just implies the sequence continues indefinitely. So I'm going to tackle a couple of the questions in the number 1 type problems, and then we'll look at some of them in number 2. So as we said, the initial term or terms have to be provided. So in the case of part A, this is a very simple sequence. As we'll see, the very first term is 11, and that's indicated as t sub 1. And the nth term, that's how we would pronounce that, the nth term, t sub n for part A, is in words the previous term plus 2. And the previous term, of course, is 1 less than n. So that's how we interpret that. Okay? So it's a little bit different at first glance when we're looking at recursive procedures, but we have seen this before. And another way to write this in function notation would be to say that the function value at term number n would be equal to the function value for term n subtract 1, and then we'd be adding 2 to that. Okay? So it still requires us to take the previous term and add 2. So previous term value plus 2 equals next term. That would be a way to interpret that. All right, so we want to start with 11 as our first term. So term 2 will be term 1 plus 2. That's going to give us 13. Term 3, well, 3 subtract 1 is 2, so that means it's taking the previous term value, which is term 2, adding 2 to that. Okay, well that is what? Term 2 is 13. So 13 goes in for term 2. We're going to add 2, we're going to get 15. Okay, this is a really simple example of a sequence. By the time we've established the 4th term, you should be able to see here that we're going from 11 to 13 to 15, and this is going to be 17. Okay, so that is going to be 15 plus 2, which is 17. So this is certainly a familiar type of relation, which of course would be linear. So our sequence would be 11, 13, 15, 17. Okay, so I'm going to pause there and give you a chance maybe to figure out what would be the explicit formula for that sequence which we generated so far. Okay, I'm back now. I just added a little bit of detail to this sequence. Recognizing, of course, that the rate of change is 2, so I'm just identifying that the slope is 2. I know that right off of the bat. The b term would be the y-intercept. Now, this is going to be a little bit tricky because, as you remember from the last lesson, the term number for a sequence always begins with 1. So we're looking at natural number term number values. So there really is no term 0, but in this particular case, if we want to model this with an explicit formula, we do need to know what we would call the y-intercept, which would be the value of the term when x is 0. Now, since x here is our term number, we're really sort of replacing y with term value, tn, and we're replacing the independent variable x with n, which is the term number. So the only changes we need to make there are just x and y for n and t sub n. So again, 9 would be the y-intercept. If we were to back up one term, from term 1 we would get the y-intercept value, which would be 9. So that would allow us to write the equation as 2n plus 9. And we should be able to test that. We know that the next number in order, term 5, would be 19. And so let's just see if in fact term 5 is 19 according to this. We would get twice 5, which is 10, plus 9, which is 19. So in this case we have two ways of generating this sequence, 11, 13, 15, 17, 19. One would be with the recursive formula given here. Another one would be with the explicit formula, which we've now identified right here. Okay. So take note, a linear function, linear relation, is going to have a very simple recursive sequence, which is going to take a term value and add or possibly subtract numbers. So let's look at another example here. We'll go back up to the set we had before, and we're going to look at this example in part B. Maybe I'll have you pause right now and just work out the first 4 terms in this sequence, and then I'll summarize the work once you've done that. If we wanted to determine what type of relation would model this, we've made the connection that, as we've seen before, a linear relation has a very simple recursive sequence, which is previous term added or subtracted, possibly from another number. And in the case of this sequence here, we could look for increase or decrease of a constant amount. I think we can rule that out right off because it's certainly changing by a lot more at first, and then the difference starts to drop off. As far as first and second differences, we could analyze that as well. Ratio might be one thing to look for, and of course, well, we could see by the way we're calculating this that we're dividing previous term by 3. So clearly the common ratio must be a third. That's linking each number to the next. So that tells us that this is a exponential type of sequence. And so if we were to consider what we know about exponential functions, we know that they take on the form f at x equals c a to the x. And in this particular case, we have to keep in mind that 729 corresponds to term 1, 27 corresponds to term 4. So again, what did we establish in our exponential chapter? C represents what we would have called the y-intercept. The y-intercept, of course, is always when x is 0. So if we want to model this with an explicit formula, I'll change the notation subtly here. I'll call it t sub n equals c a to the n. Then c really represents the value, the term value, when n is 0. Well, of course, n is never 0 in this sequence. So again, with explicit formulas, we're quite often having to search for numbers which are not found in the sequence itself. The previous example we looked at required us to find a y-intercept when in fact the sequence doesn't have one. So we can still work out the value of c, and of course if we were to do that, we would have to reverse the common ratio. Increasing term number applies a common ratio of 1/3. So decreasing term number is going to apply a common ratio of 3, which means that the mystery y-intercept here that we'd be looking for would be 3 times bigger than 729. So that is going to be our C value. So we can work that out. I'll just go ahead and pause this. At this point, you can try to figure out the base value A, and then we'll summarize, see what we've come up with for this type of recursive sequence. Okay, back again, looking at just wrapping up this question. I'd just like to point out that, of course, this question doesn't ask us to solve for the recursive formula, rather the explicit formula. I'm just taking this opportunity to show you some connections from the previous section, so bear that in mind. All right, so we've worked out the y-intercept, which is our C constant. It's going to be 3 times 729, which is 2,187. Our common ratio is, of course, what the base value is, and we've already identified the common ratio moving forward in the sequence is 1/3, which means that our explicit formula would be nth term equals 2,187 times 1/3 to the power of the term number. All right. Now there's some other examples here in this question set. I'm not going to use this time right now to show how we would substitute, although I would just maybe ask you to try C and D on your own and take note of some of the differences that you're seeing here. The recursive procedure is getting a little bit more complicated. We have multiples, positive and negative also in part D of the previous term, and we're also actually adding an extra value to the nth term, which in this case doesn't depend on previous terms but actually the term number. So as the properties have been defined, successive terms are generated from a procedure or rule applied to previous terms, and I could also point out that applied to previous terms and possibly the term number. That would be, I think, worth adding to our note here. Okay. So going back to question number 2, here's an example where, okay, we're given a sequence. We've got to work out the recursion formula. So let's have a look at some of these. Let's start with the first one. What we saw before is that for linear relations, the common difference can just be brought in to the recursive formula as a sum in this case. So just kind of pointing out that in a linear relation, the rate of change is a multiplier of the independent variable, but in a recursive formula, no longer appears as a multiplier. It's going to appear as the term we're going to add. So we're going to get the previous term and we're going to add 3 to it, and that will generate all of our terms. Let's look at the sequence in part B. I'm just going to stop here and give you a chance to try to work out. I'll get you started. Term 1 is 3. Term 2 is 8. Term 3 is 15. Term 4 is 24. Term 5 is 35. So what we're really trying to figure out is how can we get 8 from 3, 15 from 8, 24 from 5. If we were to look at term 2 as being term 1 plus 5, term 3 as being term 2 plus 7, term 4 as being term 3 plus 9, finally term 5 as being term 4 plus 11. We now have a way of relating each term to a previous term and something being added to it. Your task right now, if you try to work this out, is to figure out how are each of these pairs of numbers that I've underlined, 5 compared to 2, 7 compared to 3, 9 compared to 4, and 11 compared to 5, how are they related? Give you a chance to work that out and see if you can come up with the recursive formula. All right. Well, If you struggle with this a little bit, that's okay. I'm showing you these examples so you'll be able to recognize, in this case, how these types of sequences and these types of relations are modeled with different recursive formulas. So the linear is pretty straightforward. In the case of the second sequence, that is in fact quadratic. And the change in the term number here would be 8 subtract 3 is 5, 15 subtract 8 is 7, we get 9, we get 11. When we go to the second differences, we're taking the change of those values, which I'll just indicate as delta sub 2. Okay, that would be 7 subtract 5, which is 2, let 9 subtract 7 is 2, and 11 subtract 9 is 2. So because we have constant second differences, we know that this is second degree, which must be modeled by a quadratic function, something with an x squared as the highest power of x. All right, so that said, we're not trying to work out the explicit formula here. Here we're trying to determine how each of these numbers that we've added to the previous term is related to the term number. Well, 5 is twice 2 plus 1. That works. 7 is twice 3 plus 1, and that pattern continues. 9 is double 4 plus 1, and that must mean that we've stumbled upon a bit of a pattern with quadratic relations. You're going to see quadratic relations are going to require that any term is based on previous terms, and plus, in this case, what did we say? We said twice the term number plus 1. All right, and that works for us in all cases. So really we actually have a more complicated type recursive procedure which involves both previous term and the term number, which we'd seen before in question number 1. I'm going to have you go to part C here, and we're going to try to work out this one and give you a chance to try to set up a similar type of model to the relationship between a term and a previous term as I try to show here. Well, this is what I've come up with so far, and I'm not at a standstill with the solution, but I've recognized at least that the amount that I'm adding is not linear. I'm adding 7, 19, 37, and 61 to the second, third, fourth, and fifth term values. So that's, well, over here, definitely not linear, but is quadratic. And so here we have a case where, all right, we're going to be having to revisit, well, a quadratic sequence produced a term recursive rule which took previous term and added a linear expression. So we might be able to predict that if a linear sequence takes a previous term and adds a constant amount, and a quadratic type relation takes previous term and adds a linear amount, that is in the form mx plus b, we should be able to predict perhaps here that a cubic, and I know this is cubic because these are all the cubes of the term number, that a cubic relation may require us to take a previous term and add a quadratic expression. And the only thing I can say at this point is good luck if you want to work on this. We could challenge ourselves and tackle this in class tomorrow. But keep in mind you do have some tools at your disposal. You do know how to find the equation of a quadratic relation. We looked at that in chapter 1. It did require us to have zeros and a third point, which we don't have here. But if you're willing to tackle it, try to keep in mind some of your tools. You do have certain forms of a quadratic relation, which you may be able to use. You have a standard form, you have vertex form, and if you think you can get any of that information from this table of values, I would suggest that you try to relate the number that you're adding, which are these values here, as the y value, to the term number. And I would suggest that if you're attempting this, you're going to maybe use term number 2, term number 3, term number 4, term number 5, and try to match those almost up as an xy ordered pair. So if you face a cubic relation, it's one that's definitely going to involve a little bit more work, but we'll have some practice with those perhaps in our assigned set tomorrow. Let's turn to one that's a little bit simpler, and I think this would be a good one to finish off with, which was part D, which has a common ratio. So I'm going to give you a chance maybe to set this up as we had done before with the same format. List all your terms and try to list the terms relative to a previous term, and you're looking for the mathematical rule that is going to help you find that, and then hopefully you can come up with a recursion formula. Okay, class, we're almost done here. This last example should equip you with the skills to be able to determine recursion formulas rather from a given sequence, and we've already looked at how to determine terms from the formula, so this will kind of round off your skill set for this second lesson in chapter 6. So again, you should have your solution worked out here. Term 1 is 2, term 2 is 6, which, well, that's 3 times term 1, and term 3 is 18, and that's 3 times term 2, and it doesn't take me very long to figure out that every term is going to just be equal to 3 times the previous value. So that is an easy way for a exponential type sequence. This would be one that would have a formula that would fit, explicit model, Tn equals c times a to the n. And here we could look at, for the recursive formula, much simpler. The nth term is equal to 3 times the previous term. So there's a recursion formula, and exponential type sequences are, of course, going to be unique in that they are going to involve a multiplier. So we're not going to be adding anything to our previous terms, we're going to be applying a factor. And in case you're trying to figure out how you would describe the explicit formula for this sequence, keep in mind term 1 is the first term always, so we would have to, again, apply a little bit of reverse ratio to this sequence, which in this case is growing by 3, which would mean that the previous term, if there was one, which we could say represents the y-intercept, would be a third of 2. A third of 2, of course, is 2/3. So that means that we've identified the common factor c in our explicit formula. The base, of course, is the common ratio, which is 3, and that means that explicitly this sequence is modeled as the nth term equals 2/3 times 3 to the n. You can verify that that would generate term 5, which is 162. Term 5 is 2/3 times 3 to the 5th, and that would be 2/3 of 3 to the 5th, which is 243, and I'm kind of hoping my math is going to work out there, but you can check that that would in fact be the case. So to wrap this up, we've been looking at recursive sequences, we've defined the properties, we've looked at examples that allow us to find sequences from a recursive formula, we've looked at how to get the recursive formula from the sequence, and I just make a connection here with what we had looked at much earlier in chapter 3 when we saw the Fibonacci sequence come about with our little animal population simulation. It was 1, 1, 2, 3, 5, 8, 13 as a continued sequence, and this is one of the most famous examples of a recursive sequence. It's very simple, and it's kind of unique because it actually has 2 initial terms, because it doesn't grow at the beginning. It's 1 and 1 again, so we have to actually list 2 initial terms, and then of course any term can be found by the sum of the previous 2. So Fibonacci sequence is also one which can be modeled recursively. The sample or chapter problem rather for this section is rather interesting as well, and again we're working with fractals, and here's a shape which we'll check out in class tomorrow, but this is called the Sierpinski triangle. It's a really interesting fractal which you can create when you answer question number 15, and that's where we'll finish. See you tomorrow.